Hello, this is a cyclic variant of the Erdos-Szekeres Theorem. My name is James Schmidt,
And I'm Alex Sietsema.
and we are both undergraduate students at Michigan State University.
To start with, we'll talk about sequences. We define a sequence as being a list of distinct integers. So, for example, we could have 1, 4, 2, 5. We can also talk about subsequences, and a subsequence is a not necessarily consecutive sequence contained within a sequence. So, with the above example, we have 1, 4, 5 as an increasing subsequence. Now, in 1935, Paul Erdős and George Szekeres proved the following theorem. They said that any sequence with length at least r times s plus 1 must contain either an increasing subsequence of length r plus 1 or a decreasing subsequence of length s plus 1. Now, for an example, we'll think about sequences of length 9. We know that since 9 is equal to 4 times 2 plus 1, by the Erdos-Szekeres theorem, every sequence of length 9 contains either an increasing subsequence of length 5, which is 4 plus 1, or a decreasing subsequence of length 3, which is 2 plus 1. And here we'll check a few examples. So if we have 172, 598, 346, we have 983 as a decreasing subsequence of length 3. For this one, we have 984 as a decreasing subsequence of length 3, noting again that it doesn't have to be consecutive. And finally, we can have an increasing subsequence of length 5, 24589. And we'll note here as well that it can also have a decreasing subsequence of length 3, in this case 863, so it's possible to have both. Now, this is also the minimum possible length that has this property. So if we have a sequence of length 8, we can find one that doesn't have either an increasing subsequence of length 5 or a decreasing subsequence of length 3, namely 5, 6, 7, 8, 1, 2, 3, 4.
Now, this is not a property unique to permutations of length 8 or 9. In fact, we can always find a permutation of length r times s which does not contain either an increasing subsequence of length r plus 1 or a decreasing subsequence of length s plus 1. This means that the Erdos-Szekeres theorem defines a tight bound. Now, the classic example of this is the tilted grid. So in this example, we have r equals 5 and s equals 3, and the permutation is 11, 6, 1, 12, 7, 2, 13, 8, 3, and so on and so forth. Now, we can see that this particular permutation has no decreasing subsequence of length 4 or increasing subsequence of length 6, because if there is an ascent in a subsequence, then the two numbers must come from different columns, and there are only r columns. Similarly, if there's a descent, the only two numbers in the descent must come from different rows, and there are only s of those. Therefore, the longest increasing subsequence can only be of length r, while the longest decreasing subsequence can only be of length s.
Now, our variant is cyclic, and we define a cyclic sequence as being a series of numbers which wraps around. So what this also means is that if any two sequences are a rotation of one another, they're the same. So for example, 1425 is the same sequence cyclically as 4251. And working with cyclic sequences, we've come up with a cyclic variant of the Erdos-Szekeres theorem. And we say that a cyclic sequence with length at least r times s plus 2 must contain an increasing subsequence of length r plus 2 or a decreasing subsequence of length s plus 2. And now, for example, if we use the sequence 148372556 cyclic sequence, and we have it length 8, which is 3 times 2 plus 2, we should have either an increasing subsequence of length 5, which is 3 plus 2, or a decreasing subsequence of length 4, which is 2 plus 2. And immediately it might not seem like it does, but since it's a cyclic sequence, we can find the decreasing subsequence of length 4, 8, 7, 6, 1, where we wrap around from the 6 to the 1.
Now we shall provide a short proof of this. So let's consider a cyclic sequence pi with length rs plus 2. And let's write pi as pi 1, pi 2, all the way up through pi rs plus 1, and then finally c, where c is the largest value in pi. Now let's consider the subsequence pi 1, pi 2, all the way up through pi rs plus 1 as a linear sequence, which will have, of course, length rs plus 1. By the Erdos-Szekeres theorem, this subsequence must contain either an increasing subsequence of length r plus 1 or a decreasing subsequence of length s plus 1. And so let's call this subsequence that we have found pi I1 all the way up through pi it, where t is just r plus 1 or s plus 1, depending on whether the subsequence is increasing or decreasing. And so now, if that subsequence is increasing, pi I1, pi I2, all the way up to pi IT, and then C will be an increasing subsequence of length R plus 2 because C is greater than all of those elements. And if it is decreasing, once again, because C is greater than all of them, we can rotate C around to the beginning, and now that will be a decreasing subsequence of length S plus 2.
Now, just like the linear Erdos-Szekeres theorem, this cyclic variant is also a type bound. So in other words, that means that there is always some cyclic permutation of length R times S plus 1, which does not contain either an increasing subsequence of length R plus 2 or a decreasing subsequence of length S plus 2. And here, we'll just show an example that this is in fact true. And though it's difficult to represent a pi that has this property in a clean form, we can draw it as a diagram. So for this example, we use 1, 12, 7, 2, 13, 8, 3, so on and so forth, where we let R equal 5 and S equal 3, and so the 1 hanging out in the bottom left is the lone one that we get for R times S plus 1.
Now, this example may look very familiar, as the S by R tilted grid is the exact same example from before, just with a 1 to the bottom left. And it is fairly evident that if we begin an increasing subsequence and a decreasing subsequence with that 1, we cannot create an increasing subsequence of length R plus 2 or a decreasing subsequence of length S plus 2, as there is no increasing subsequence of length R plus 1 or decreasing subsequence of length S plus 1 inside of that grid in this rotation. But if we ignore 1, then we only have to deal with rotations of that tilted grid. And once again, considering the columns, we can see that every time we have 2 successive elements in an increasing subsequence, they, as before, must either come from different columns or must loop around from the end of the rotation to the beginning, such as the first and last element is in the increasing subsequence 2, 3, 4, 5, 6, 7. Now, since this can happen at most once, since otherwise we would not have a proper subsequence, this means that the longest possible increasing subsequence must have a length of R plus 1. And we can do this exact same argument with the rows to determine that the longest possible decreasing subsequence must have a length of only S plus 1.
Now, the Erdos-Szekeres theorem can also be framed in terms of pattern avoidance. Now, cyclically, we've also proven results for avoidance sets of pairs, triples, and quadruples of cyclic patterns of length 4. Anything higher becomes trivial. In addition, our other work includes examining cyclic shuffle compatibility and generating functions for cyclic permutation statistics.
We would like to thank Dr. Bruce Sagan, Quinn Minnick, Rachel Domagalski, and Jintang Liang, with whom we collaborated to find these results. Thanks for listening.